So for cold open, I just have Isaac Arthur.
Isaac Arthur. He's back. Better than ever. It's good. What I like about you, Isaac, though, is that you were like, all right, so we're talking about wormholes today. What was the other thing we're talking about? And it was like, oh, teleportation. And you were like, oh, yeah. Like you just know, like you just have this stuff in your head. You're like, oh, yeah. No, I got that covered.
It's no problem.
Yeah.
Every time I think if I were to build a rule in my head, and if Isaac's cool with it, it'll be that every time it's like, oh, we have to do an episode where I have to know physics. Well, I know who to go for that.
Mm-hmm. So welcome back to this show. We're
glad to be on.
Yeah, we're very happy to have you here. It's going to be like a live corrections episode where normally Tristan says some stuff and then a couple months later we'll issue some corrections, and this time we've got you right here to just be like, actually, I think the first time we had you on we mixed up general relativity and special relativity, so that was very helpful.
I'm trying to avoid using the word actually to start sentences off anymore. Actually.
Well, you can just be like,
especially with that specific inflection, actually.
But yeah, I feel like it's been a long time since on this podcast. By the way, internet, this is a podcast called It's Probably Not Aliens.
That's right.
Called It's Probably Not Aliens, where we talk about pseudo-history, pseudo-archaeology, and ancient astronaut theory, usually responding to ancient aliens. My name's Tristan Johnson, and I know very little, but I did a lot of research. This is how we know the topic is going to go places. I did several days of research on this episode, and I know nothing about this topic.
My name is Scott Icewander. I'm the other host of this show. I know even less than Tristan does. If you can believe it, that's true. Mm-hmm. And we have a returning special guest, Isaac Arthur, who I have to imagine has done more than a couple days of research into physics in general. Is that true?
Yeah. It's. I think you need years to study on physics just to actually get to the point with quantum mechanics that you don't feel like it's just weird and nonsensical. Yeah. Eventually, at some point, it flips over to being intuitive. So.
Oh, well, that's good.
And then they let you out of the asylum.
Yeah, I'm just imagining that like the first day of like third year of your physics major, and you go into the class and they're like, all right, guys, listen up.
Yeah, it's going to get wonky.
Remember all that math you knew before? Well, all right, we did one side of physics, fine. Now we're going to do the other side. And by the way, we still don't know how they meet. So let's go.
Can I ask you, we were talking about Marvel movies before the show started. Can I ask you how accurate, if you've seen it, how accurate is Ant-Man and Wasp Quantumania when it comes to quantum physics and such?
Not very much. I actually ended up doing a Quantum Mania episode as a joke, Multiverse Warfare and Quantum Mania, that would come out the same day, and it didn't do very well. So it's like much like the movie. But I'm a big fan of Kang. He's like my second favorite Marvel, villain after Doctor Doom. Mm-hmm. And maybe Apocalypse, but he's right up there at the top.
Yeah.
And I do not feel like you really judge Marvel movies by how accurate their science is, because the answer is
probably a good idea.
Don't even start. The first Marvel movie is literally, I invented a magic energy machine.
Yeah.
Occasionally you'll find like Star Wars, Warhammer, things like that. The science isn't very realistic, but sometimes they will land on something very accurate. And Marvel's had a few here and there, but mostly, again, it's like going into a Michael Bay movie. You don't go there for the realism.
Right.
I'm actually curious. It's actually curious, Isaac. I wonder how annoying it is to people who do four-dimensional geometry work, how much Marvel has messed up the word for a 3D shadow of a 4D hypercube.
Tesseract.
Oh, yeah.
Somewhat ironically, I was reading that up in a script recently. It was the example people would have. They did that with, it was an old show, Threshold, from the early 2000s, had Brent Spiner and Peter Dinklage in it. So it was a bit of a gem. Otherwise awful, but it could have been done better, but it was okay. It was Brandon Braga on that one, too. I had some good points, but they did a Tesseract that would pop into the universe, and it had the magical power of brainwashing people into, like, alien zombies. So they're really not that good of an example of how that would work. There's nothing all that impressive about what a 4D object would look like in 3D besides explosive. You put something that's got more dimensions into a space, it doesn't do well. It'd be like trying to stuff a tire into a piece of paper. It's going to blow up.
Yeah.
doesn't really look all that weird.
Interesting comparison.
We're learning so much already.
Yeah. Okay. So let me tell you, Isaac, why we brought you here today to live correct me on my research. So here is what's been going on. We are wrapping up talking about episode 1 of season 2 of Ancient Aliens. Yes, we are only that far through. And this whole episode was trying to make the claim that various places that have urban legends about them or just look weird might be the place where, using ley line energy, aliens had what they literally called stargates, which were doing some sort of either wormhole or teleportation or something. Let me try to get like the actual quote here that says, another theory to how extraterrestrials might have traveled across the universe involves the scientific concept of teleportation.
Oh.
But is it really possible to have something disappear from one spot and appear somewhere else? And then Sarita, at the Max Planck Institute, scientists have already dematerialized subatomic particles and made them reappear somewhere else. So science is just on the precipice of being able to do this, to move it from one place to another. So I believe that it is a secret that the ancient stone builders knew. Since wormholes are theoretically located throughout the universe, could these same types of gateways exist in smaller areas on Earth?
So yes.
Oh, why not?
It gets better.
Oh.
According to ancient astronaut theorists, by the way, this is all verbatim.
This is verbatim.
According to ancient astronaut theorists, the Gate of the Gods is one end of a wormhole, a type of portal that connects either to another part of the universe or another dimension. A wormhole is a theoretical construct through general relativity. The concept is really that there's a possibility of space-time being connected, various parts of space-time being connected through a small channel. And if such a construct was made, then you'd have a shortcut between very distant parts of the universe. You might be obliterated into a bunch of subatomic particles, as far as I can tell, but yes, you would be there. Wormholes are an accepted element of theoretical physics, but they actually theoretical's doing a lot of work there. But they actually existed in the world's most mysterious places. The idea that there are stargates, actual word they used, or that they could have existed in ancient times. You know, the big rotary phone that goes to other planets.
One of my favorite sci-fi shows ever, too.
We do see many artifacts and representations of someone passing through a doorway. I have some other interpretations what that could be, or going through some type of energy source. An ancient man did not understand technology, just as they were trying to understand. Is a wormhole possible? And then we finish off with David Childress. That is some kind of doorway between our dimension and another, citation needed. And what I maintain is that these aliens who are going through here are coming here in interdimensional type of craft. They're able to jump through hyperspace. Again, I think that's a word from science fiction, not from science. Come here to our planet in no time at all, but they have to enter through certain doorways and portals into our planet. So,
all right, does any part of that jump out to you as like a little, or I mean, like they nailed it, right?
No, but they could have. Yeah, I mean, well, I would say it's a great example of how pervasive Chariots of Fire was as a piece of work, and I mean because it's inspired so much sci-fi and for that matter, additional conspiracy theories. But at the same time, it's not exactly wrong because they're quoting certain things, but they're taking a lot of liberty with it, obviously. And, you can't just go and say, well, this highly advanced technology that we don't possibly understand based on science we don't know isn't possible and couldn't exist. Because, I say that no one believes it. We live in an era where the impossible becomes possible fairly quickly. So I'm not going to say you could not ever possibly use quantum this way, but every time we've had a trick that people reference as like, this will let us go faster than light, and we've investigated, the answer was a hard no, not a kind of maybe, but a hard no. And the reason why we can't investigate the wormholes thing specifically is because those almost always require exotic matter. And the key thing about exotic matter is that we call it that because it only exists on paper. And this isn't a case of like one of those things where we think we're going to find it. The big one for wormholes is negative matter, right? Negative matter. And you can use negative energy too, which is a little bit subtle. But negative matter is the idea that something has mass that is negative, which means, that works on paper. So, but the math works out. That's great. You can have a negative dollar in real life, right? Hand me a negative dollar, though. It doesn't really exist. What's a negative piece of chocolate?
Right.
That is a piece of broccoli, if I remember correctly.
In math, you can have a negative piece of broccoli. In practice, That's just an accounting thing. Yeah.
Yeah, I do love this mathematician thing where it's just like a mathematician will say like, well, if we have this thing that's literally impossible, then we could do this. And everyone's like, you see, if we could just find the impossible thing, then we could do this.
If we could find the impossible thing, the math would mostly work out. The alternative is use imaginary math, which gets even weirder because that's like the square root of -1 matter as opposed to just -1 matter. But I mean, this happens a lot, and I'm not going to beat up on math about it. It's very valuable as a tool for theory, but at the same time, the whole idea of physics and science in the modern era is that we take experimental evidence, and from that we derive hard, predictable results. And I like string theory. It's a nice theory. I like, wormhole theory too, but all these things are based on a complete lack of evidence. So the math works out and there's not a piece of evidence for or against them. And so that's not really a good place to be basing off your, but it's kind of hard to disprove too. Someone says, well, can you show me a wormhole can't work? It's like, well, I can't prove to you that negative matter doesn't exist. That doesn't work under Popper.
Right.
This actually does make me think about how, this is a good introduction to it, but how like the whole speed of light, hard speed limit thing, I've recently come into, and I'm pretty sure you've got to be familiar with this YouTuber. You guys are in such close spaces. Sabine Hassenfelder.
I know. Well, yeah. I think we might have exchanged an email once too, but I can't call for sure.
Well, she made a video about the speed of light and how whether it could be broken or whatever. And she was talking about it as if it was it's more of a barrier than like a thing, because there are things that are faster than light. They're just sort of
most of the universe moves away from us faster than light. It's one of those hard things to say is like, because of Hubble shift, almost everything you can see with a really big telescope anyway, most of the universe is moving away from us faster than the speed of light right now. And you try to say nothing can move faster than the speed of light, except almost everything in reality. But the thing is, what it really can't do is you cannot move information between two places faster than that speed of light. We would call it the speed of causality, but we measured light first. And you cannot do time travel paradoxes, is what it really says. But I mean, the basic analogy I find that works better is, say, when you make something speed up, you have to add energy to it. And energy is just mass is one type of energy. So if I have a wheelbarrow, and that's something's rest mass, it's basic mass, as I try to go faster and faster, I have to add more and more stuff to that wheelbarrow. You can never actually get to the point where that wheelbarrow ceases to be part of that equation, though, right? Even if I got a million things inside that wheelbarrow and it's stacked up to the Himalayas, it's still there. And nothing can move at the speed of light so long as it still has rest mass or that wheelbarrow. So that's the basic idea, is the more energy you put in there, the harder it is to push that thing a little bit faster or a little bit further. So you have to add more energy to push it even harder. And it's just an asymptotic limit. It's not a barrier in any kind of meaningful sense that way.
That's why like all of the like actual theoretical FTL that could work is like basically just taking, if you treat the universe like a sheet, you're kind of like woofing it and you're sort of like riding the wave by just, instead of moving faster than light, you're just moving space itself to be faster. We're getting into, this is a bit of a digression, but I want to talk, we're talking about today wormholes and teleportation.
I'm into it.
The zone of silence, the Puerta da Umarca, these are places that apparently are stargates or teleporters or wormhole spots. And they're the subject of today.
Them in previous episodes of this podcast. We talked about the history of them in previous episodes, and now we're going to get to the science of it. It sounds like, what if they were wormholes or teleportation devices?
Yeah, and I've got Isaac because my last math class I took was grade 11 high school math, of which I got a B-.
Cool.
Which I think we ended at quadratic equations. So I got Isaac because Isaac actually knows things.
Yeah.
Last math class I took was when I was 19, so it's been a while.
So there's another thing too, and we're going to be talking a lot about quantum mechanics in this episode, which is a profoundly weird area of physics. But I will say this one thing. We're going to be talking about quantum mechanics. Quantum technology right now is a very hot topic in the world of science and investment. And there's untold amounts of money being poured into trying to crack quantum computing, specifically because of its implications for the world of cryptography. And so every government is pouring tons of money because if you're the last person to develop quantum computers, goodbye all of your secrets. But the other thing too is that that there's a lot of potential in here, but also some people like Sabine Hassenfelder point out that we might be at this sort of right before the sort of hype dip in the hype cycle when it comes to quantum computing. But essentially what quantum computers do, or what the main thing about quantum computers, that they can solve a bunch of stuff with that regular computers can't do in very specific ways. But the main thing I wanted to talk about is that quantum mechanics is probably highest on the list of things that have the biggest gap between the way that the public understands it and the way that it's actually understood, to the point where in some ways it has literally been used in place of magic by like cranks that are definitely in our wheelhouse, our who've determined that it's like what's that classic, What the Bleep Do We Know? Remember that one?
That sounds familiar, but I can't think of that one.
It's basically tried to use things like the double slit experiment to show that mind over matter.
Well, you can do some interesting stuff with that. Roger Penrose has played out what's it, Oracle. I'm trying to remember what that's short for, but it's a quantum. The idea that the human neuron might be at the quantum level and therefore might be, basically quantum itself as opposed to deterministic. So, which is very debatable, but also very arguable if it matters. I think the biggest thing with quantum is it becomes such a hand-wavy thing. It is the techno-babble of the modern era, while at the same time it's also really cool. And we always talk about how hard it is to understand, but in some ways it really isn't too tricky. It's just that if you're already learning basic science, it can feel really counterintuitive, but when you don't know too much science, sometimes it's actually a little bit easier to understand because you're not trying to unlearn things.
Yeah, it feels like, would you say it's like akin to maybe, how when kids are younger, they're able to pick up different languages faster, but then once, as you get older and you're like, if you only have learned that one language, it's harder to pick up a second language.
Same one for relativity is a lot like that too. It's because it's so counterintuitive to the basic mechanistic way we tend to look at things under Newtonian physics. It comes off as a little bit more complex than it is. The core thing to understand with quantum mechanics was that we have this old Zeno's paradox concept of, if I cut something in half, I cut something in half again and again, I just keep cutting in half forever and ever. If I get close to the wall by half a step and then another quarter of a step, I'll never quite get there. And we find out at the quantum level, we have things that don't get cut in half anymore. That's literally where the word's coming from. It's quantized. There'll be things like, you don't have a proton that has 1.5 proton charges or 1.5 proton masses. There's no electron with 2/3 a normal electron mass. It's all very discrete, specific. And that's what the quantum mechanics thing comes from, is the idea that when you get down that scale, there are some very specific limitations and they only fall in certain areas. And that's where the teleportation actually comes in at the basic level. It gets a little bit more complex, but even those orbital models of atoms, the electrons only ought to be in this place or that place, not in between them. So to get from one to the other, it actually has to teleport. Now, it was never actually in that specific orbit. It's smeared across the whole area as a probability thing, but that's where it gets a little counterintuitive to understand. But that's where it comes from. That it was going from A to B with no transition. And that is a great example of how that works too, is because if you're trying to understand the difference between discrete and what you usually have with numbers, just think of an alphabet. You can have 1.5 or 1 2/3. You don't have a letter that is half A and half C, or halfway between the letters F and G.
Well, what about that one letter that's like an A and E at the same time?
That doesn't count, and we're not going to pay attention to anything that comes out of it.
So basically, because of that, the reason why, so let me try to see if I can get the quantum, because quantum computers play a big role in this. So quantum computers are essentially little atoms that, so in quantum mechanics, atoms have things called spin, which they can either be spin up or spin down. The thing though is that because of the way that quantum mechanics works, where everything is probabilistic, so things can be on a range of things based on probability, which means if you don't measure where the atom's at, it can be in sort of a varied amount of up and down at the same time based on what probability it is one of those things. And so for solving certain types of math problems, specifically the reverse factoring of numbers, that they can solve that much faster than a regular computer, which, like, all right, let me see. All of cryptography is based on the fact that computers are really bad at reverse factoring numbers, except that qubits can do that. So very well.
Let's say that I have a random number generator for the moment, and I lock a person in a room with a phone book, an old school phone book. These are devices, for those who don't know, that had everybody's phone number listed out on paper, right?
Right.
Just a while that we let that happen.
I know that somebody named Dan has this phone number in the book. That he called me. Call this man and find out if it's him. He'll tell him blah if he answers the phone, and he'll recognize me, right? And so you sit somebody down inside a quantum room, like a Schrodinger's cat, and he shut the door. And during that time, he's going to randomly call someone that's named Dan out of that book. This is a conceptual example for anyone's going to get upset. The physics isn't quite right here. So while the door is locked, I'm not absorbing it. He could have called any one of those random Dans in the book and called them and made contact with them. And I open the door in a way that lets me ask the one who actually got the correct answer. Maybe I say something like, when you get the right person, open the door. And so the version of him that actually called the right Dan is the one that opens the closed box and collapses the wave function. And hi, I got him. He's right. It's Dan Bartholomew, right? 8675309. We got him. But this is the tricky thing with quantum is the simple concept is I'm doing a manhunt. I'm trying to find somebody who's in the woods, right? We know where he started at, and we know how fast he can walk. So we have a circle out to the time where, 1 hour, he'd be 3 miles away, right, from walking. He could be anywhere in that circle, and there's a probability of where he'd be. And we say, well, yeah, he could be anywhere in that place, but we know he is at one of those places. But when we find him, we know what place it is. The only difference with quantum is we're saying that person or particle could have been anywhere inside that area, and we don't know until we check it. But the difference is he actually was in all those places simultaneously until we actually checked it. It wasn't where he might be, it's where he actually was. And that's the counterintuitive aspect. But when you have 50 billion coins, you're flipping heads or tails or dice you're throwing, that gets very normalized when you start looking at how it often comes with heads or tails. And that's the whole thing is we were made out of trillions upon trillions of particles. So the fact that they're smeared all over the place except when checked doesn't matter statistically. It's just like an election. It doesn't matter if Bob or Tom down the road might be voting for Jack Johnson or John Jackson. Statistically from the polling, it's going to come out very close to that one number. And that's basically in all existence. Even the cellular level, things are mechanistic because of, that statistical Pauli effect of the quantum stuff. It just factors out. But that's the one counterintuitive aspect to really understand about quantum is where we don't know for sure if the cat's alive or dead till we open it up in the real world. In the quantum world, it's because it really wasn't. One way or another, it could be A or B. And that's the only real difference you have to get.
Well, I was going to say, I know you were worried about that example, people being like, maybe it doesn't check out scientifically or whatever because it's a hypothetical example. I have great news on that front, which is that we're talking about ancient aliens, so I don't think people are super concerned about their science mathing out too much, and I think yours makes more sense so far.
Well, it can vary because for a lot of folks who follow the conspiracy stuff, as we'll say, they are usually all pretty interested in the science. They're just mostly interested in the science that appeals their interest better, I'd say. I'm often on a lot of shows that are what you would call more paranormal, and they love their science too. They just have certain parts that they care less about. For me, it's great sci-fi. For them, it might be real. Some of them, they just enjoy it as an idea. But obviously, they don't appreciate being poked about whether or not their theory is very realistic. But then who does?
I getcha. That's fair. I don't know if Tristan has this on his outline, but I'd love to ask you this question because it feels like the idea behind some of these sites, they're like sort of sites built by stone workers back in ancient times. No real like electronic technology, obviously, but people are claiming them to be wormholes, stargates, things like that. What's the possibility that a wormhole could just appear out of nowhere? Without people making one.
The infinite probabilities issue is we tend to assume that there's any wormholes that are already in existence. They'd be from the inflationary era right after the Big Bang, which is also still disputed in theory right now. But the idea being that when the universe was about the size of a basketball or a car, it's in between atom size to basketball size, very tiny, or at least all portion of the universe, because it might have been a bigger one outside it, that there would have been, at that scale, what would become the galactic scale would also be still tinier than an atom. And if you have a little place where the electron would be orbiting between, say, its A state and its B state, that tiny little micro nanometer space, that would blow up to something that would be at the galactic scale nowadays. So if something had popped up there as a rupture or a defect in space-time, that could have stretched out to be a wormhole nowadays. So that's one of the ways you can get to wormholes. There's a lot of different wormholes or wormhole-ish like ideas, and we usually are referencing to the Einstein-Rosen bridge. That's not the only one. That's just the one people tend to hear about, and that's the one that's got, I hate saying it this way, the most theoretical basis to be reality, except that it has no evidence into reality.
So we were just talking about quantum computers, right?
Yeah.
We're talking about
and sort of-
Stonehenge, I think, but yeah, that's somewhere. Is Stonehenge a quantum computer? Probably not.
But basically, because of the reverse factoring thing, quantum computer, the first person who can figure out quantum computers, the first team that can figure it out, is basically going to break every single way that we store passwords and secrets everywhere. And there's now like sort of a race to try and find something that is even a quantum computer can't crack, basically.
Mm-hmm.
You can do that. The thing is, the same technology that lets you do the super cryptography stuff with quantum, which is kind of overhyped, is the idea that you can also use that same concept to generate uncrackable stuff from quantum, cryptography. So it is not the thing that's going to end all secrets. Privacy is always in danger. I don't want to downplay that, but almost all of your real hacking issues come down to people just being careless with their own passwords and data security. It's not, we have unhackable stuff right now. We have options like one-time pads. Quantum computer does allow you to break things like that. It just lets you break your to the 256-bit type stuff. So you just have to change over. We have methods that would be immune to quantum cryptography that are already in place, or already exist, I should say, but they're not as efficient to use against other hacking methods. And there's better to use right now, the ones that would be. So if we start getting quantum computers that can do this, we just shift into using those other ones. And probably not an issue for another decade, I'd honestly think. But when it pops up, it could be an issue for a lot of existing stuff that people had not actually bothered to switch over the cryptography on.
Well, as you well know, Isaac, things not being a real technology for several decades yet has not stopped people from investing tons of money in it or getting very hyped about it for no reason. Just look at my Google alert for fusion power, for an example. So the first topic we're going to get into is teleportation, which there's only really one type of real teleportation that we've been able to do, and that is quantum teleportation. Now, here's what I'm going to start with. I'm going to start with Isaac Arthur's, who I feel like is a reliable source on a video that you did on teleportation. So here's a little bit that we got. First, the reason why teleportation is probably a big deal is because of Star Trek. Basically, due to budget constraints, Star Trek implemented the transporter, and it's sort of become a staple of sci-fi. Another example, I think you were talking about how this was set up to promote a TV show. In the novel Altered Carbon, teleportation involves transmitting digital copies of the mind to an awaiting copy, which is, it's sort of cheating, but I get it. But basically, the idea is that in that form is that you would record every single atom and isotope in a human body and transport it somewhere, which would basically require an insane amount of data, basically more than any functional computer could actually really have, at least at this point, unless you're like, using a Matryoshka brain or something to process a transportation, which is a computer powered by an entire sun. So you might be able to do data compression, but there is going to be issues. And trust me, if there's one thing you're not going to want to be lossy data, it's going to be teleportation. You don't want to be the human version of a JPEG.
and I think that is the key thing with it is how much compression will be okay. Because if you're trying to send a human in terms of like every atom state, does it really matter if the DNA for one cell in your body was not a 100% perfect match for the DNA that came over? And, your mileage might vary, but for the most part, your DNA doesn't match across your body perfectly anyway. You can really compress something like human DNA, especially one person's. You don't need a trillion DNA bits sent to somebody. But when you get to the brain, that's a little iffier, and there's a lot of debate as to how much actual memory there is in the brain and how you record that. But then in emphasis, you're always copying there, and this is what gets around the no cloning issue you have with other teleportation. You're sending a copy. That might be a very popular way to teleport people in the future. Say, send me a copy of the brain and put on Android for me somewhere. Or, what do they call them, sleeves and Altered Carbon and other people. You might do things like that. And you probably do a lot of compression on a human brain for that matter, too. It takes a lot of data, though. And do you really want that floating around through space where someone could presumably hack it, intercept it, etc.? So you got to keep a copy on hand. Now you got another one of you. Teleportation in physics, though, and talking quantum teleportation, that doesn't, that's not making a copy somewhere. That's actually, you're changing your state of some other atoms that exist. Like, if I quantum teleport a person, I'd be turning some existing matter that was at that location into a configuration that was identical to me. So if I'm teleporting into a room where Scott's at, I'm suddenly tuning into Scott. Scott is, by the way, he's tuning into me. Kaboom. And this is trickier than people tend to think because you can change the state of any atom into another atom. There was a technical finite probability of various atoms turning into other atoms. So they might turn into one molecule of chocolate, and they could theoretically turn into an entire candy bar, possibly complete with an apple. It was a finite but ridiculously tiny number chance of that happening. The other thing, though, is while that's happening, these physical processes are releasing a lot of radiation, for instance. So you might be popping up into a place, and yes, you've appeared, and everybody around you has been blown up by a gigantic equivalent of a nuclear bomb as it goes up. However, there would still be a finite, albeit ridiculously tiny probability that every last one of those gamma photons that came out from your existence as you changed all those atoms around would miss an atom on the way out, that they would just not hit something. Your odds that I'm standing in the middle of an atomic explosion and not a single particle hit me. There's a finite probability of that happening. So that's where multiverse stuff gets a little bit weird, because there should always be a large number of universes where you didn't get hit by a single gamma photon. Or maybe I hit by 10 of them, maybe one randomly hit you. There should be billions upon trillions of universes where teleportation absolutely does not work, but people think it do because they hit a switch and randomly a copy of them appeared on the other side of the planet.
Yeah, it just
by
happens.
Coincidence. And it happened a million times in a row every time they try to check it, so they believe it.
I did like in your video, though, that you also mentioned that you could use it to, say, teleport out cancer or get immortality, or the most fun one is as a interesting weight loss technique.
It's totally underutilized in science fiction. It's like the replicator. It's one of those things you just shouldn't have put into the setting because it's so breaking, Yeah,
you might make Thomas Riker or something.
That was like a piece of beta canon where he got imprisoned by the Cardassians during the Dominion War or something.
We need more Thomas Riker stuff. But so the other thing, though, is that as you mentioned, the teleportation that we actually have been able to witness is basically can we do teleportation? There are two answers: either yes, we've done it several times to quite impressive degrees, or no, and it's unlikely we're going to do it anytime soon. Those are the two answers, depending upon what you mean by teleportation.
Right?
Because you can, and we have teleported quantum information, which again we're going to get into a whole different kettle of fish with that one, but you can do it via quantum entanglement, but it is not faster than light, and it is destructive by nature and requires a channel, which therefore makes it so that it can't go faster than light. Because the only other than that, you're just
Well, you can only send trivial data, and I mean it's easy enough to demonstrate as a concept. I should point out we definitely can do teleportation. The sun works on teleportation. That's how fusion works, but it's very short range. With teleportation, imagine I addressed a letter to two people. Inside one was I said, inside this letter is either a red or a green piece of paper. I've sent two copies of the letter. One's got the red, one's got the green. They are entangled, right? That I sent them at the same time, and I open one of these copies up, and I'm sending the other one to Alpha Centauri, and one was being sent to Epsilon Eridani, 10, 15 light years away. And when you open that letter up, instantaneously, faster than the speed of light, you know what that other person's letter says. That is quantum entanglement. That information, that spooky action at distance effectively too, as an analogy anyway, that doesn't in any way help you communicate faster than light anything else, though. You just have that one trivial bit of information. When I get that particle and I say, aha, these entangled particles, mine is up, so the one that was sent to the other guy has to be down.
Yeah.
Now, the fact that transmitted is weird. That's the spooky action bit, but that's conceptually what's happening, why you can't send more information with it. That's all.
To kind of build on this, so in your video, Isaac, you also propose another form of teleportation, which I found very amusing, which is that you can use nanomachines, tiny machines, to basically just tear you apart atom by atom and put you back together like some sort of Lego kit.
Yeah.
But you did mention that doing so would basically be akin to like setting off a small nuclear explosion. Because you're basically tearing apart all of the beta bonds in our bodies and just...
Also, I imagine the amount of screaming that would take place while someone's being teleported also is a little unsettling.
Disintegrated by robots.
Well, I think the idea came from Pushing Ice? It's a novel by Alistair Reynolds, which is probably I will not spoil it for anyone, but definitely worth looking into. He does great hard science fiction, but it's just mentioned as kind of a throwaway there of somebody teleporting that way, where basically they're full of nanotechnology, and that nanotechnology has a way to rapidly grab every last bit of them so they can suddenly be rapidly accelerated at ridiculously high speeds and reassembled on the spot. And that, it's viable. I think he does something like that also in his House of Suns book for their equivalent teleportation. It's not fast and light, but hey, if I can get from here to Germany in 5 seconds because I can have my, particles accelerated at 5 million G or whatever it is, that's close enough to teleportation for me.
That's close enough.
Love me some Alastair Reynolds. Alastair Reynolds wrote my favorite short story.
Which one?
Beyond the Aguila Rift.
Oh yeah. And
who doesn't want to be caught by a Lovecraftian space spider, but then be tricked into a fun vacation while happening? Anyways,
he's definitely in the Lovecraftian vein for a lot of his works, but this is an example like with Wormholes 2, they're not instantaneous. People think if you go through a normal worm sword, again, this is the Einstein-Rosenbridge version, is like, I step here and then I'm out there. No, you have a transit time. Those tunnels are long. They're not even necessarily shorter than the real space journey. They are through space, and they take time. They can be weeks, months, years, millennia. They're not instantaneous.
Yeah. The other proposal you put forward is that there's something called, and I did not do the deep dive into this, but you mentioned something called meson, specifically a kind called a neutral pion that can fly through normal matter uninterrupted before decaying rather explosively.
Yeah. This is a problem you have with a lot of things in particle physics. Mesons are, they are two quarks, basically. And this is the same for a lot of the other ones. The two quark combinations opposed to the three quark ones that us and other more stable particles are made out of. But a meson can basically just pass through anything. And that's not really unique to these mesons, if some wouldn't. That's not really unique to them. We have other ones like neutrinos that will pass through, like a light year of lead, they like to say, without being likely to get intercepted. But there's a lot of things like that in nature that do that. Dark matter, for instance, say, well, dark matter is weird. We can't find any examples of it. It's like, well, it's hard to find an example of a neutrino too. But there's a lot of things in nature just don't interact with certain forces that much. And the weak nuclear force is called that for a reason. It's one of the four fundamental physical forces. And it's a lot weaker than the strong or electromagnetic force. Way stronger than gravity still, but it's very weak. And it is positive and negative, and basically your odds of having two particles intersect each other is ridiculously low in that contect. So they just blow right through each other like it wasn't there.
I think when you do that, it's called nuclear fission.
Well, right. Well, that's what happens in supernovae. Is you actually have a situation where things are dense enough that you can actually have weak interactions having a meaningful factor into things. That's kind of how we get a lot of the heavier particles. Although a lot of stuff is not made in the center of supernovae like we tend to think that it happens like neutron star modules, etc. And that's another place where things are dense enough that you can have these weak interactions taking place at a regular level. The same for the early universe and the Big Bang situation, which is how we get a lot of these very more exotic potential particles or constructs being made. And I think that the key thing with the weak force is, say, if I were to turn something into those particles, there's the idea with the mesons is, I'm going to convert you into this state, right, where you're made out of mesons or you're made out of dark matter or neutrinos. It's not that you're going faster in light this way, it's that you're going through anything at all. And this might not be the best way to teleport a person, but be a great way to teleport a large packet of energy into a bunker or ship. It's going right through their armor and blows up. And you're the best armor in the world. You can have Wolverine-style adamantium covering every last pinch of but it just goes right through. It's your face sword, as it were, and pops up and blows you up. That's the best usage of teleportation with a ship like that. It's not to send people over, it's to send bombs. You say, well, we're going to send a boarding party. And anytime you can send a boarding party, it's so much easier to just send a bomb.
Yeah.
Never get that. Never cover that one in Star Trek. Yeah, I always that's one thing about Star Trek I always think about with teleporters. It's just like, or transporters. It's like they never factor in that you could transport somebody like without consent, and the ramifications of what you could get away with that are terrifying.
Especially the copying version. You make a copy of someone by teleportation, Thomas Riker style, and they're your prisoner that you're keeping to do whatever horrible things you're going to do to them, and nobody even knows because the copy of them or the original them is still walking around. But the scary thing is you could have something like mind uploading too, where you just take a copy of the mind and putting it into a virtual reality or clone or an android.
Yes, I also have watched Black Mirror. Yes.
Oh no.
Black Mirror basically covers like the dark ramifications of mind uploading in several episodes.
The only episode I've seen is the first one with the pig.
Yeah, that doesn't cover in that one, but you might like San Junipero. I think it won an Emmy.
I'm afraid the pig one scared me off the show a bit.
I will say the pig one was an odd choice to start the show off with.
It'd be like
weird. although given David Cameron's biography, it turns out weirdly prescient. Anyways, but yeah, there's an episode called The Black Museum, which shows like a lot of the horrible ramifications of mind uploading. Yeah. Anyways, or also the Christmas special. The Christmas special's terrifying. It's got John Hamm. Great episode.
As every Christmas special should be.
Yeah, it's the most terrifying. It's a Christmas special of a show that to this day still occasionally gives me nightmares. So the last teleportation use case you mentioned was something called what you dubbed hammer space, which would basically just be that you could keep all like tools and like objects that you need in like hammer space, basically just like a big warehouse somewhere, and then you could just teleport it to you whenever you need it.
Oh yeah. Yeah. And then there'll be the one like it's the question is this an extra-dimensional universe, like an infinite magazine for your gun, or are we talking about a refrigerator door that opens up onto this icy moon where you keep your food at because screw electric bills, I just have a portal in my, and then I think was it Dan Simmons and Hyperion plays that a lot, where people have houses that are literally each room is built into a different place in, light years away because they gotten that cheap with teleportation and wormholes at that point, or, portal space. I think Rogers Lazzy did something similar to that in his Courts of Chaos Amber series, the second half. But the idea that you're just knitting together entirely different sections of different planets to build your home in. And say, well, if you can do that, this is when you have a technology in sci-fi, you always want to think about that ramification. It's if you can do that, if I can teleport you from A to B while teleporting a bomb. And in the J.J. Abrams Star Trek reboot, from what was that 2009, where they have the warp travel or interstellar teleportation going on, and it's like, well, you can now teleport from one planet to another. Why do you have starships at all? What would be the point at that point?
What do people need with a starship?
And then Peter Hamilton's Commonwealth saga, they'll say with the wormholes, you have these stargates. Why do you ever shut them off? There's a 38-minute rule in Stargate series, but you got the running all the time. So now I have this portal going. I don't send people through. I run a train through there on a fiber optic cable. It's got a train track. It's got fiber optic cable. We run heat condensers through there. We run power plants on the other side. I got some wasteland place somewhere where I have all my giant nuclear reactors, and I don't even bother being safe with them. They're just pumping out the radiation because we just bring back through giant superconducting cables right through the wormhole. And kind of the same thing, I want to terraform a planet. Well, it's like, I need to get water on this planet. Where do I get it from? There's a water planet over there. Why don't we just go ahead and
take some of that? Thank you very much. You're not using it, I'll use it.
The same for power plants. You say, why not just sink one into this into a star? And maybe it's a tiny wormhole that big. Although that might not be quite as effective as people think. Stars are very low power in their cores, but in terms of how much they're actually producing, they're like 1 ton of matter produces enough to run a light bulb.
It's just that there's a lot of tons.
A lot of it, and it's very hot. So.
Yeah.
I've heard stars are very big.
Yeah.
That's just a rumor, though. No one's ever actually seen one in person, so I don't know. So basically the idea, though, quantum teleportation. It's a way of transferring quantum information from one location to another, but doesn't really work for physical objects, really. Kind of?
You kind of maybe... You could potentially... if you can build a big enough quantum computer and get big enough entanglement, then in theory you could move an entire person from point A to point B. And this is the thing is, there's no theoretical limit as to how far that can go, and there's no theoretical limit as to how many of them there can be. But that's kind of like, got to have a context on that, saying like, with a big enough level, I could move a planet. Until we actually build something that can, be a big enough level, you don't really notice all the mechanical strain issues that might pop up in there. A lot of the question of, where's my fulcrum going? Where am I putting this level? Am I putting it over the top of the moon? How does that work?
I think it doesn't help that I feel like the trend for technology right now is making everything thinner and smaller. We're not going to get a big enough computer. Everything's going to be thin and light. We're going to be able to carry it around in our backpacks. We can't. We're never going to build
a little tiny chip. Then you suddenly teleport a much smaller object from point A to point B. But you don't have to at that point. You just send the data. But, I mean, there are options for it out there. Do I know any scientists who think you'd ever be able to teleport a human over your distance with quantum anything? No. Yeah, it's basically I say, well, I can figure out how to move a stick, therefore I can move the galaxy. So you just kind of assume that there's going to be some real limitations on this, starting with the sheer amount of data you have to move. And we can't just always handle that at quantum computers because... these two concepts do not stack.
Yeah.
I did see though while I was doing research for this that there is the first case of an object that they were able to make entangled that was large enough to be seen with the naked eye, which is like a huge feat. So just showing where we're at on this.
Interesting.
It was like a piece of sapphire, I think.
Oh, cool.
Well, what's neat about a lot of materials is you can actually get the entanglement's basically about, let's try to think of a good way to phrase this. This is always hard with quantum. You can get relatively large objects. You can, like a graphene atom, right? It is entangled. You can send that together as a chunk. That's 60 atoms. or was it a buckyball? There's no real limitation on that. And metals like, well, I shouldn't say metals, items like sapphire and diamond that are very, very tightly organized, you can actually potentially treat that as one large object that could move as a group. But the thing about entanglement is the big one is people kind of want, that's the teleportation idea, is that they don't have to be entangled in advance. So that's kind of what they're aiming with a lot of stuff, is the idea that you wouldn't actually have to all those entangled. The other thing to keep in mind, and this is a big one that comes up, is once things are entangled, once I check them, right, one time they're no longer entangled. So if I have two particles or any atoms like that are entangled, the moment I check their position, e.g. complete the teleportation, they're no longer entangled. So you can't go backwards again. Say, well, now they got X and B way over across the side of the galaxy. They stopped being entangled the moment I measured them. That entanglement was what I basically said, oh, okay, I snapped that to make the process work. It's done.
Works once.
Yeah.
So there's some sci-fi that misunderstands quantum entanglement to be like that it could be some sort of like superluminal method of communication.
Yeah.
But
communicating
not only
that one thing, envelope
One
AOB.
time.
It can only be that one thing, but also basically none of the knowledge you could get that out of that would be any different from random guessing, because it's going to come out as basically random.
Right. Yeah. All you're finding out is I got envelope A or B, and I know the other guy got B. He's got the red envelope. I got the green one. That is all you get to learn out of that process. And because believe me, we try. People have spent decades trying to figure out, how do I make this thing give me some other piece of info? It never has worked. And people are certainly welcome to keep trying, but there's just, all the obvious ways you think of to try to get that to work. You say, no, and you go through the math, nope, that wouldn't work at all. No. All you get out of that is A or B. And as soon as you got that, it's done.
And that is essentially called the no cloning theorem?
Close enough, yeah. The no cloning theorem is the idea that, well, basically you can't clone a particle at a different location. If I go ahead and make a state of something, like if I quantum teleport you onto Scott, suddenly Scott turns into you.
Scott is always the victim of teleportation accidents.
I'm like sitting over here changing into multiple people. Like, I just
like a little Tuvix over here. He's the Tuvix of this podcast.
Oh God, that was actually a good episode of Voyager. I would say that was a pretty good one. But especially for the early seasons, the moment that I make that copy of you elsewhere, you have to cease to resist in that process. Which is one reason why it's interesting for copying purposes, is because one thing you don't really want is that Thomas Riker situation where you have somebody left over on the pad. It didn't quite happen. You got two of you now, because then you have to pay both of them.
We should probably tell. I realize Scott, Thomas Riker was an episode of TNG where they had a
Next Gen. That's the only Star Trek I've seen.
But Thomas Riker is like one episode, two actually.
But it's a good episode. I know that episode. Then you've seen it.
Okay, never mind.
You can explain it for. Let me
for
see
the internet.
For the exposition piece, the audience. There's an episode of Star Trek where many years before he showed up on the Enterprise, a lieutenant commander or Lieutenant Riker, I think he was lieutenant at the time, had beamed down to a planet, and they had promised teleporting him back up, and they did some strange stuff with lifting the safeguards to teleport him, and the beam bounced up, and part of it bounced back down and rematerialized as him, while another part came back up. So there's a copy of him down this horrible planet, barely alive, until they found a signal and picked him up. And he was very angry about, about 8 years of life having missed him.
And he turns up as a random villain in Deep Space Nine later.
That's fun.
But experimental studies have shown that quantum teleportation can be performed using different objects like photons or atoms or certain circuits, as long as you're willing to get them to a temperature that is slightly above absolute zero, so that they have no electrical resistance, otherwise known as a superconductor.
Yeah. It is very difficult to get. Well, most things in life like to bounce around and move around and really don't compile very well for the purpose of trying to precisely measure them, which is what you really kind of need in a quantum setup. So, and this is another one of those issues. Would you like to teleport? Yes. First, we must freeze every atom in your body in a way that doesn't kill you, and really freeze it too. Not like Antarctica or even like Pluto, like places nowhere in the universe would be that cold. It is a lot of the tricks with things like this. It's very hard to get things to stop moving. And
I think they did it with Walt Disney's head.
Yeah. Apparently, I grew up believing that was true, but it turns out that he does not have his.
No, it's not. He's cremated, I think.
Yeah. That was so disappointing for me.
It's the opposite of being frozen. It's being cremated.
Yeah. He did the thing. He did what's it called? He did what the little nanites would have done. They just didn't put them back together.
Yeah.
So the other thing is that in order to do this, you need to. All right, let me see if I can get this. Let me see if I can remember my own writing. Like I said, I've gone to some weird places in my brain to do this. So the resources required for quantum teleportation involves generating an entangled Bell state of qubits, performing a Bell measurement, and manipulating the quantum state of the other qubit from the pair. The protocol involves generating a Bell state, performing a Bell measurement, and sending 2 bits of classical information and modifying the Bell state qubit at the receiver location.
All right. Was that good? Did Tristan get it?
It works for me. I am not an expert on quantum computing. I did an episode on it, and it has gone in like the 4 years since that. I've barely looked into it beyond that.
Yeah,
it's definitely improved, but it is one of those things where it's a fascinating new area of how they do the research on it. But it's not the most overhyped thing in science's history, but it kind of is really up there. So
right below cold fusion.
It both is and isn't. Yeah, and cold fusion also.
There you go.
Yeah. It's one of those things.
Future, right? It's one of those things that looks very, very exciting until you can't tell where the field is going or how exciting it is until you observe it, and then it collapses, and it looks like
right.
It
is the Schrodinger's cat of science. And again, this is one of the issues I tend to have with like string theory and anything with quantum too. Is it gets so overhyped in the narrative and so many of the resources in it because they would like to get their papers published better. They'd like to get more money for their field, so they tend to play a lot of the hype a little bit. And I don't want to criticize them too much for that, but nobody should ever be talking string theory with the public because it's not like there's not enough there to make it real. It gets people confused and think this is what all scientists believe is true. The same for things like mini-worlds theory versus Copenhagen, which the Schrodinger's cat experiment is Copenhagen interpretation of quantum. Mini-worlds theory is the one where it says there's a universe where he's alive and another one where he's dead. These are all contradictory theories. They can't both be simultaneously true. Even in quantum, they can't simultaneously be true, which is always everyone's next question on that. A lot of these other theories exist for it too. The thing is, they all say, yes, we predict the results perfectly. Is there any evidence this theory is true? No, not one bit of evidence. Same for string theory. We don't know how quantum actually works yet. So everything with quantum, we talk about quantum computing, what its limits are. We don't know because we don't actually know how quantum works. We know exactly what it does. We can predict what it does very well. That's the easy part, ironically enough. But we don't know how it actually operates. So you get these limitations. Say, I don't know if this is actually possible because we don't really know how this works yet.
I do love when we talk about this kind of stuff that it does seem like every few years, all of these scientists who are like fighting over papers, like it seems like it's the source of many a bar fight at random conferences. And then every few years they have to get together in a city and be like, all right, guys,
what's going on?
We have to figure out what the hell's going on. And then they come together with a consensus that then immediately falls apart the second the scientists leave and do their own experiments. I think the Copenhagen interpretation was like a bunch of people came together and be like, all right, guys, we got to get our story straight on what this is going to be. And then they came to a conclusion that immediately, I think there's also one for string theory where a bunch of string theorists came together and were like, all right, this is the theory. Then immediately that fell apart. Speaking of string theory though, I got to know what the beat on this guy is. So another interesting frequent guest on Ancient Aliens is Michio Kaku, the apparently like one of the big founders of string theory. And it's just like, does Michio Kaku just say yes to anybody? Is that his thing?
I will not speak to that too much because I go on every show too. If somebody invites me,
well, yeah, you're here. This is Bob. Yeah,
I'll do paranormal shows, things like that. I'm probably fine with it. Just speaking to what the science is. He is a big one for string theory. He certainly is good at what he does, but what shows he goes on, that's not necessarily indicative. That's more of a flavor style, right? Okay. My philosophy is I go, if I'm going on a conspiracy show or something that's not necessarily a very pro-science channel, I'm going to go proselytize to the heathens, as it were, because you don't need to speak to the choir. Man, what I mostly found a lot of those things, though, is with the paranormal groups, they're usually all very into science. They're just maybe they've decided something that's more from science fiction for you or my point of view that we enjoy as science fiction is more likely to be science fact. But except for those places where they have a break with it, with the observable science because of what they afford to believe they're usually very pro-science. They might not know tons of it, but then some of them really do. And the other thing is a lot of times, you'll have just as many problems with more science-oriented groups as they don't believe something that actually has turned out to be true. They're a little bit too skeptical. So I would say, going back to him real quick, what shows he goes on, I'm all for going wherever you want to go to talk to people and explain the real science to them. I would not, however, say that string theory really qualifies as science at this point. That's the issue. Ooh. It's not that, and that might have said Sean Carroll too, but it's not the people that aren't scientists. They really are. They're really great. I'm fond of string theory too in many ways, but it's not science at the moment. It's just a theory based on math that draws on existing science to be its basis. It can potentially predict things very well, but there's no scientific evidence of it. And this is where you get the kind of the popular view of how we do science. If I can't find evidence of something in the material universe to back it up, I can't say that I'm actually doing science. That doesn't mean that it's not thought, doesn't mean that's not deep philosophy or even accurate. It might be true. It's one of the best theories out there for these things. Same for Copenhagen or same for mini worlds. You might say, well, you can't be saying that Copenhagen or mini worlds are real science. So yeah, that it gets iffy. Where's the line between how much speculation is possible? We would absolutely go get data if we had any way of doing that data. But the problem is we can predict things under many different quantum theories, who are presumably contradictory, that accurately predict the results. I don't think you can make that argument with string theory as much. This does not in any way diminish the theories. The problem is they've been overhyped a little bit too much in terms of everyone thinking they follow. These are very great researchers, and I'll probably get some hate mail over that, but it is what it is. Those theories themselves cannot be said to be scientifically proven, and since there is no current model for falsifying them, they're not science, although that's a debate that some folks have been trying to have recently.
They're very good at math.
Yeah, they're very good at math. I don't think they disagree with me on those points either. They probably, prefer different phrasing on it. Sean Carroll actually wrote a really good article on why we need to move the term science to start including things like that. Because not that they disagree about getting evidence, is that they just don't see any framework for being able to get it, and they feel you should be able to speculate about these things from a scientific standpoint. It's a good argument. I just don't happen to agree with it completely.
So from what I can pick up from when it comes to quantum computing and teleportation specifically is that it's starting to get used because one of the major issues with quantum computers is something called coherence, which is essentially that for a computer to really function properly, it basically has to never, ever make a mistake. And qubits have
40% of the time.
qubits have an issue where the entangled states and stuff that they make to solve things sort of falls apart after a few seconds. And if you add too many atoms to the system, it gets sort of harder to keep things going, and you need more and more. You need like more stuff, keeping it even colder, and it just gets nasty. So they're thinking of using teleportation to just create kind of like how when we hit the limit of what we could use with CPU cores, then we just started adding more cores. And so they're trying to use teleportation to sort of network between different qubit systems to sort of do that. And so that's interesting. The recent advances that I wanted to cover are that at Stony Brook University, there was this breakthrough in energy teleportation where an IBM supercomputing quantum computer was able to mitigate errors and observed a successful transfer of energy as well as negative energy, which has potential applications in the study of gravitational field and quantum field phenomena.
Yeah, and we were talking about negative matter earlier, and negative energy is kind of the slightly more real version because we have something called the Casimir effect. All current, if you ever looked at the mass of an atom and you say, well, that's made of 3 quarks, each of those protons or neutrons is made of 3 quarks, and you look at the mass of those things, you look at the mass of those quarks, you say, wait, that's off. I got a 2 MeV and 2 MeV and 4 MeV, and those add up to 1,000? How does that happen? Because most of the mass and energy there is being made up of what we call, C quarks as opposed to valence quarks. And the idea behind quantum is you got stuff that's constantly popping in and out of existence. Always constantly popping out of existence. And this is about as true and proven as we could reasonably get with that. So we kind of accept that as a pretty solid one. But when I have things constantly popping in and out of existence, much like when I have photons going through a location, there's always light photons going through you, they're migrant. On a freeway, nobody lives on a freeway, but there's always traffic there, right? So there's a population density on a freeway. Kind of the same thing with this quantum vacuum is that you always have things popping in out of existence. As a result, there's always a constant state of energy there, even when you say everything else in the area. But if I put two things really close together, because everything has a wavelength, every particle, everything has a wavelength associated to it. If I got two gigantically flat plates near each other, anything that's got a wavelength bigger than those plates are away from each other cannot form or exist. They can't be there because their wavelength is too big. As a result, because they're not forming in there anymore, but they're still forming on the other side of it, you get a pressure on the outside of the plates pushing them together, right? And that's the negative energy concept there. So it's negative compared to the background state of the universe, but it's kind of like saying this is the ground floor that we all live on, and therefore we have negative height by saying there's a basement. But the basement's not really negative height, it's just below the level we were at. If you go and start things at the basement level, then everyone on the ground floor is on the first floor. That's negative energy.
Now, if I remember correctly, and I think you've talked about this in one of your videos, that there is, if like that messing with that, I mean, there's a theory that if you were to get that too low, you could hit a point where basically it would just unravel the entire universe.
But the theory holds that it happens at light speed. So if we did it in the Andromeda galaxy, it would still take 2 million years to get to us. So it is possible that
that's their problem.
Waves of destruction.
Yeah. We'll deal with it later. That's fine.
It's like climate change. Some Elon Musk will fix it somehow.
Someone down the line will figure it out.
Well, the good news on something like that is we said most of the universe is moving away from us faster than the speed of light. So if someone in a galaxy 10 billion light years away did this, that collapse wave would never actually reach us. So
we'll send our 0-point energy that way. There you go. We'll make a wormhole that goes to that place, and we can have our 0-point energy there, and then we can send the thing through and then close the wormhole when the vacuum, what's it called? The vacuum decay thing happens?
Yes, but
there you go.
Of course, this is one of the ways you potentially make wormholes is with the Casimir effect and that negative energy. Because what you're basically trying to do there is the compressive force of a black hole is supposed to rip a hole in reality. What you are saying that with is the negative energy or negative mass which you put a throat through, right? You're showing up a tunnel that way, and that's what you're supposed to pass through. So, and again, on paper, this does actually still work because whatever the actual ground state of the universe is, whether that's zero or not, if you can have a state that's below that, even if that's the true zero, the universe is still up here. So in theory, you could go beneath it. And that's where that one potentially comes in as slightly more realistic as opposed to negative matter, is that you should be able to potentially go underneath that false vacuum layer. Now, to know that even better, you would actually have to go talk to one of the people who's an expert on that, which actually would be Michio Keiko or Sean Campbell. So,
I will mention to people out there, this might be the
stake at the moment. They know their stuff very well.
I'll mention to the internet people that this is like I'm talking about stuff that like this thing that they were able to do this to mitigate. They're trying to use the Casimir effect to mitigate errors in quantum computing. This is like stuff that got published like a month ago. So keep in mind, it's still really wonky.
Stuff's happening.
Yeah, I should add, I haven't read yet, so I can only talk to it to some much of a degree, unfortunately.
Yeah. The other one is that there was a big advance in the field of quantum communication by successfully teleporting something called a Q-trit, which is a quantum trit. What a trit is, don't know. But apparently it's a unit of quantum information that's realized by a 3-level quantum system that may be in superposition of 3 mutually orthogonal quantum. So is this like 3-way position? Is this the positioning of a 3-way?
Help us.
Is this 3-way position? Help us.
You can have computers that are built on trinary, right? And usually they, instead of having your on off, you would have 1, 0, and -1 as your states. And presumably, I'm just going to, because again, I've not read up on that. I would guess the Q-trit's the equivalent of a qubit in that kind of context. It'd be a 1, 0, and -1.
Perfect.
Well, we actually have this with quantum flavors. As we have red, green, and blue as the colors for quantum, and quarks come in flavors which are a little bit weird. They're up, down, top, bottom, and charm and strange.
This is a lot of sex terms.
Yeah.
Quantum 3-way is there's a top and a bottom, and
these are very
and a switch in the middle.
Assigned things, but we literally named it the strange one because it was strange. So.
Yeah. Speaking of another thing that's apparently going to destroy the universe.
Strangeland, yes, yeah.
Strange. So hopefully we came to a satisfying and knowledgeable conclusion about where we are when it comes to quantum teleportation.
Can't imagine we have.
Can I just say we're over an hour into this podcast and we've only talked about teleportation. We were going to talk about wormholes as well. I feel like seeing as how much you've written so far, Tristan, that would take us like a full other hour. I'm good to just call it here and just make this one about teleportation, if that's cool with you.
Would you want to do a part 2 next week? That would be fun.
So I think next week we're going to get to wormholes, which I'm very excited about. Like the wormholes in like a space-time sense, I guess. I don't like when you take a bite, when you bite into an apple and you find a wormhole. That's no good. No one likes that. We're not talking about that.
No one likes biting into a universal apple and finding half a wormhole.
Exactly. And we'll pick it back up with Isaac then. Isaac, thank you so much for joining us for another very, I was going to say complicated episode, but you have a really good way of explaining things in a really simple, sort of elegant way for people like me who don't really know anything. I feel like my brain has grown 3 sizes since the start of this episode. So thank you so much for being here.
Oh, so we're glad to be back on.
Yeah.
And so, but at the moment, this both is and isn't, and semi is and semi isn't. It's probably not aliens. And you can find, not find, or semi find our Twitter, depending upon what Elon does with Twitter the next week.
Who knows?
At Probs Not Aliens on Twitter. So basically, it's Schrodinger's Twitter. In one universe, Elon has killed Twitter. In another universe, Elon hasn't killed Twitter. And we'll see where it is next week.
We just don't know. Yeah, Isaac, where can people find you online if they want to search out more of your stuff?
You can find me at isaacarthur.net or online at YouTube or on iTunes, Spotify, etc. Just search for Science and Futurism with Isaac Arthur. We have a new episode every Thursday morning.
Absolutely. Good stuff. Tristan, how about you? You have stuff that you work on.
Yeah, I have a YouTube channel called Step Back where I talk about why the past is important for understanding the issues of today. And right after this podcast, I'm going to go and talk for probably another 2 hours about cultural Marxism. And hopefully by the time this episode drops, that'll be out. So
fantastic. Sounds like a very light topic. Yeah.
Scott,
yes.
If I wanted to learn about why you're not happy about the state of your content right now, where would I go?
I have a YouTube channel called Nerdsync, NERDSYNC. My latest video is literally just called I Don't Think I'm Happy. And it's just like an update about my creative process, but I'm getting there. I'm doing some good stuff. Hopefully, I'm just going to start pumping out episodes. And I was very inspired by this podcast, being able to make something every week with you and just have it be fun. I want to do that for my YouTube channel. Go check that out. You can also find more of this podcast over at nebula.tv/probably not aliens. By the way, if you're not listening there, the second episode about Wormholes is already up.
Yeah. If you think about it, signing up for Nebula at nebula.tv/probably not aliens is like, it actually is superluminal travel because you are traveling a week into the future.
That's right.
And getting next week's episode now.
That's what we were trying to say in a very roundabout, confusing way. Thank you to everyone who wrote reviews of this show on Apple Podcasts, and for everyone who's told their friends about it. And a very simple link you can send people to is probsnotaliens.com. That's where you do it. Until next time, my name is Scott Nicewander.
I'm Tristan Johnson, and the truth is out there, or it isn't out there, in a certain probability wave function, and you have to collapse it to find out. I over Heisenberged, I think, the outro there.
We will find out if the truth is out there as soon as we open up one of those envelopes, and then we'll know. Yep. We'll know what happened.
Excellent. No one's going to find that annoying at all.